Morning, everyone. My name is Mustasin Sakif, and I'm a doctoral researcher at Tampere University. So this paper was a collaboration between Aalto University from Helsinki and Tampere University. And Aalto University is the one who provided these polypyrrole-coated conductive yarns for testing. And in Tampere University, we did the fabrication and embroidering and testing of the RFID antennas. So eTextile is kind of textile which has electronics in it. So of course it would have conductive yarns, which is very essential to make interconnection between different electronics. Generally, conductive yarns are metal-based, for example, copper or silver-based. And RFID technology is very essential to eTextiles because it has a lot of application, including identification and tracking. So what is a polypyrrole? So polypyrrole is a polymer which is synthesized through pyrrole monomers, and it has many known characteristics, but the most important ones that we are concerned with is the high conductivity, its ease of coating with different substrates, and its durability. So because it adheres to different substrates with ease, we can use this conductive material to coat different yarns and fabrics, in turn making them conductive. And at the same time, it makes the material durable and flexible as well. So how do we coat a yarn with polypyrrole? So first we need pyrrole, of course, and we need iron chloride. And in this case, we have used stencil yarns. So the first stencil yarn is soaked in deionized water, and then iron chloride is added into the water, and then the pyrrole is mixed with ionized water and slowly dropped into this solution. The reaction happens for several hours. And in the end, we get this yarn, which is rinsed and dried, and then we get the yarn. Now that we have the yarn, we need to make the antennas. So in the figure, you see this is the antenna geometry that we have chosen, and this is a straight dipole antenna. And with this polypyrrole coat yarns, we made two sample antennas. One is with pair 1, one is with pair 2. The substrate used is Iannacchero. This is 100% cotton. It has holes in the substrate, which makes the embroidery easier, and at the same time, the coating does not get removed while embroidering. And the process used was only the outside geometry of the contour, so we get the most amount of performance with the least amount of materials. And the IC used here is NXP code series IC, and it has copper platings, two sides. But normally, when we fabricate RFID tags, we either use adhesive materials or we seal the copper pads with the conductive yarns. But in this case, because we want to make the yarns reusable, we sealed over the contact pads. But there are several factors that influences the wireless performance. One of these is the important thing is the electrical conductivity. And in this case, we'll see how the conductivity is affecting the overall performance. The structural design is remaining the same over the antennas, and the density. And finally, we are comparing this polypyrrole-based conductive material with the silver-plated yarn, which is 11034. So how do we do the testing? So we put the RFID tag inside the anechoic chamber and do the measurement using a warranty tag performance measurement system. So in this system, we send out a signal and measure the backscatter signal. And we take the measurement from 850 to 950 megahertz. And with this equation, we can measure the read range. So read range gives us the understanding of how far we can read the tag from. But before we get to that result, let's look at the electrical and mechanical comparison. So first we did the yarn tenacity measurement. So tenacity is the maximum amount of force required to break a yarn. And in this case, the tensile yarn itself would have like 33 centinewton per peg, but after the coating, the polypyrrole yarn has 42.7, so the coating increased the durability. And the silver yarn is rather brittle, which is 20.5. We also measured the resistance of the yarns. And in this case, silver yarn has a much lower 500 ohm per meter, but the polypyrrole you can see is like 0.3 mega ohm per meter, which is like 60,000 times higher. That reflects in the wireless evaluation. So if you look at the read range versus frequency, we see that the read ranges for the silver based yarn antenna is performing around 3 times higher at a frequency 866 megahertz, which is the European central frequency, and 915 megahertz, which is the US central frequency. In both cases, the two polypyrrole antennas are rather similar, but there are minor differences. I would say the result is pretty practical and usable, although it's not as the result is not as great as a silver-plated one, which is rather usable. So what are the reasons behind these variations? Embroidery is very difficult to replicate. There's imperfections in sewing and elasticity of textiles. Another reason could be like when polymerization, there is uneven coating, which could lead to some differences. As well, when we're embroidering, there could be some removal of polypyrrole, but the differences are pretty insignificant for the result. So what key points can we take away? So of course, silver-based yarn exhibits superior performance, read range, conductivity, but the polypyrrole-based yarn has lots of advantages. First of all, it has higher tenacity, which means it's strong. It can endure flexible and lightweight applications. It is more comfortable on the skin. It is ideal for embroidery machines. But most importantly, it has very low environmental footprint. It's very cheap to make, sustainable, and it has versatile applications. So in future, we want to enhance the doping and the coating processes so that the conductivity is improved. So we could have even more applications, but most importantly, we want to make these coated yarns washable. which is very important in wearable and textile electronics. Thank you, everyone.